Welcome to the Harbor Branch Education Center. My name is Ned Smith, and as you can see from the title slide, the topic today is an introduction to the climate of Florida's Treasure Coast. In this first slide, there's an outline showing what I would like to cover over the next 45 minutes or so. There will be a very brief introduction in which I make a distinction between weather, which we will not be talking about, and climate. The two are directly related to each other, but I will be focusing on climate, and I want to make sure that I draw a line between the one, which I am talking about, and the other, which I'm not talking about. And then we'll go through 5 characteristics of climate. The two principal characteristics are temperature and precipitation. But in almost any area, there may be another meteorological variable, or 2 or 3 in our case, that are important enough so they should be included in an introduction to climate. And here I'll be showing some slides on the wind patterns that exist along the Treasure Coast, the humidity, certainly during parts of the year. The humidity is an issue. It can make being outdoors at certain times of day anyway quite uncomfortable. And then finally, cloud cover. This next slide makes the important distinction between weather and climate. I will be talking about climate. I will not be talking about weather, but I will mention weather just long enough so that you know that I am intentionally not talking about it. Weather is what you would observe on a particular day. A particular day might be warm or cold or rainy or dry. Whatever you observe, whatever you record on that day is the weather. Climate is the average of the weather. If you take a particular day, May 1st, for example, I think will be the example that I give in the next slide. If you observe the weather on May 1st of one year, May 1st of the next year, May 1st of the year after that, and average all of those May 1st readings, you get the climate. Anytime you hear the term average, you know we're talking about the climate. So the climate then is a measure of what you might expect because it was averaged from observations on that particular day. Now the example, and I mentioned May 1st, I could have chosen August 12th or January 21st or whatever. But for May 1st, you might go to the beach and record a temperature of 76 degrees in 2016. You could come back the next year, same place, same day, and record 74 degrees, and then the 2 years after that, you got 2 different temperatures. Those are the observations. That's what you record on that day. That is the weather on each of those 4 days. If you average those 4 temperatures, you get 75 degrees, shown over on the right, and that is the climate. It's the average of the observations. Because the climate is based upon observations, the climate is often taken to be a starting point which gives you the best estimate of the weather that you would record in coming years. Here in this next slide, we have the 2 fundamental characteristics of climate: temperature and precipitation. Temperature can range anywhere from very warm to hot in the tropics at the low latitudes to very cold or cool, very cool or cold in the high latitudes, the polar climates. And then in between, in the middle latitudes, oftentimes over the course of a year, there will be seasonal changes from cool to perhaps cold in the winter months to warm and perhaps hot in the summer months. Similarly for precipitation, there can be climates like the rainforest, which would be wet almost the entire year, perhaps the entire year. At the other extreme would be the desert, which would be dry during the entire year. But just as temperature can range from warm to low seasonally, precipitation can range from wet to dry, wet seasons to dry seasons, seasonally also. And we will see when we get into our temperatures and our precipitation that we have distinct seasonal variations. Now, there can be other meteorological variables which are important enough to include in a characterization of the climate. And three that I'm going to cover here involve the wind, the cloud cover, and the humidity. But I'll get to that when the time comes. As I go through the characteristics of the climate here, you should keep five things in mind, five fundamental factors that are important in determining the climate that we have. We're at a low latitude. We're not tropical, but we're almost tropical, and that goes a long way in explaining the relatively warm temperatures that we have during much of the year. Much of Florida is at a low elevation, and generally speaking, the warmer temperatures are found at the lower elevations. You have to go to a mountain peak or a mountain top or at least high elevation somewhere to get into the cool and cold temperatures. We have an ocean nearby, just offshore here, the Atlantic Ocean, which tends to stabilize temperatures over the course of a year. Now the ocean warms up during the summer just as the land area does, but the ocean doesn't warm up as much. The ocean cools off during the winter months, but it doesn't cool off as much as the adjacent land areas. So if we have winds coming in off the ocean, the warmer temperatures in the summer months won't be as warm as they would be without the ocean there. The ocean has stored some of that heat, and the cooler temperatures during the winter won't be as cold as the land temperatures would be if we did not have the ocean, because the ocean is giving up some of that heat. Ocean circulation patterns, the Florida current offshore here, which sometimes is referred to as the Gulf Stream. It's not really the Gulf Stream, but the Florida current. The Gulf Stream starts a little further to the north. The Florida current, though, comes past our coast out of the south from even more tropical areas. If the Florida current were moving from north to south, it would be bringing cold water down from the north, and it would be cooling our climate significantly more. But the Florida current is warming our climate, is keeping things just a little bit warmer by providing this constant supply of warm water from further south. And then the large-scale wind patterns. We have onshore winds during much of the year, not all of the year, but much of the year. And it's with those onshore winds bringing air that has been warmed or cooled by the ocean that we have a more stable temperature along our part of the coast here. So the latitude that we are here, about 27.5 degrees, is not quite tropical. As you can see from over on the extreme left part of the slide here, the tropics, the true tropics are anywhere between the Tropic of Cancer in the northern hemisphere and the Tropic of Capricorn in the southern hemisphere. We are just outside the Tropic of Cancer. We're about 281 miles north of the Tropic of Cancer. The Tropic of Cancer is a little bit south of Key West. It's a little bit north of Cuba in the Straits of Florida. So with that as introduction, let me begin by talking about air temperature. And I'm going to start with a regional comparison, comparing our annual average temperatures in Florida with the annual average temperatures recorded in our two neighbors to the north, Alabama and Georgia. The blue curve at the top of the plot is the curve for Florida, and we can see that it stands out distinctly above the two curves for Georgia and Alabama. We're about 8 degrees warmer than the annual average temperatures recorded in the same years in those two states to the north of us. We have warmer temperatures here because we're a little bit further to the south, we're a little bit closer to the tropics, and also because we're surrounded by water to the west by the Gulf of Mexico and by the Atlantic Ocean to the east. Looking at the local picture here, I'll just mention this in passing. You can see the curve in the lower right is Fort Pierce annual temperatures, and there's a lot of up and down there. We have warmer years, we have cooler years, primarily determined by the conditions during the winter. All of the summers are hot, but some of the winters will have more cold fronts and would be a more intense winter. Some winters are milder. But if you draw an average line through the scatter, what you see is that the Fort Pierce annual average temperature, the long-term average, is about 73 degrees. Quite a pleasant temperature, quite a comfortable temperature. Now, Fort Pierce is getting warmer, and I didn't know where to put this slide in elsewhere, so I just put it in right here. Fort Pierce is getting warmer, and you might think that's a result of global warming or regional warming. That's not the case. It's an effect of growth in Fort Pierce. As Fort Pierce becomes more urbanized, there'll be an additional parking lot put in here and an additional paved street put in there. The paved street and the paved parking lot causes rainfall to run off more quickly and into the canals, into the rivers, the creeks, and then out into the ocean. But because rainfall runs off more quickly, it's not available for evaporation. It doesn't soak into the soil as much, at least where it hit the parking lot. It's not soaking into soil there. And when that water runs off, it's not available for evaporation. Evaporation cools the air temperature, so if there is less water available for evaporation, there will be less cooling, and if there's less cooling, there's more heating. So the more parking lots and streets we have, the warmer the temperatures. There is an arbitrary cutoff between temperatures that are considered warm to hot and temperatures that are considered cool to cold, and that arbitrary cutoff is at 65 degrees Fahrenheit. If you go back over the annual temperatures for the last 70 years or so, you can show that Fort Pierce has 8 more days per year of average temperatures above this cutoff of 65 degrees than it did before 1950. And again, this is a result of the growth, the urbanization in Fort Pierce, not a result of the global warming. Now, this just repeats what I mentioned in the previous slide here. I got ahead of myself a little bit, but we have more paved areas. And I can add here that with an increase in urbanization in Fort Pierce, we have more vehicles, and vehicles, whether trucks or cars, are exhausting very hot exhaust, and that mixes with the air and warms it up. With more people in Fort Pierce, we have more air conditioners, and they are exhausting heat, taking heat out of the building and putting it outside. And we have factories. Now, Fort Pierce is not a big factory city, but to the extent or where cities have factories, factories will generate heat also, and that contributes to the urbanization effect. Our warmest 4 months, this is for Fort Pierce again, are June, July, August, and September. The bar graph here shows that the afternoon maximum temperatures all reach about 90 degrees. I think July and August reach about 91 or 92 degrees. But these are the warmest months out of the year. The yellow bars show that for those same months, temperatures are maybe in the high 60s to about 70 degrees or so, and then the average is given by the blue bars. We can use the temperatures, the average temperatures in any given month, to define meteorological seasons. And these are the meteorological seasons for Fort Pierce as defined by temperature. Now, the last slide shows that the 4 warmest months were June, July, August, and September. And we can see here that those same 4 months stand out as the warmest 4, so they become what is called the meteorological summer. The meteorological winter begins at the end of the year in December and then continues into January and February. Color-coded in green is meteorological spring, and those are the 3 months when things are warming up. And then at the other end of meteorological summer, on the other side, is the meteorological fall. You can see that things cool off relatively quickly over about a 2-month period, whereas things warm up relatively slowly over a 3-month period of time. This slide is kind of busy, and it includes some weather. I'll just mention that in passing. The yellow curve at the top is the extreme temperature day by day, 365 extreme temperatures recorded over the course of a year. The green curve at the bottom are the extreme low temperatures. Now, these extreme highs and lows occurred just on one day, when on that particular day it happened to get just a little warmer than it had at any other in any other year on that same day. But that's the result of the weather. So here in this talk we should focus upon the red curve and the blue curve, which are the average high temperatures and the average low temperatures day by day over the course of a year. And we can see a certain similarity here. The average high temperature gets up to about 90 degrees or so, and at that same time of year the average low temperature is rising to about 73 or 74, maybe 75 degrees. At the other end of the year, January, February, our average high is in the low to mid 70s, and the average low is in the low to mid 50s. We had a weather station here at Harbor Branch quite a number of years ago, and I've just chosen 1 year out of that long weather record. It was a year in which the weather equipment operated flawlessly throughout the year. They won't always do that, but in this case I had 365 1 a.m. temperatures, 365 2 a.m. and 3 a.m. temperatures, and on throughout the entire day. I was able to average, and here's average, so you know we're headed toward climate. I was able to average the 1 a.m. temperatures, and that is the first bar that you see over on the left. I averaged the 2 a.m. temperatures and so on through the entire day. And what we see here is the tracing out of an average day, cooling and warming and then cooling again. What surprised me when I first plotted this was that we warm up from the coolest temperatures, which are about 7 in the morning, just right at about sunrise, to the warmest temperatures, which are at 1 o'clock in the afternoon, 1300, 1 o'clock, over a period of just 7 hours. And that's when we have relatively clear skies and we have relatively intense heating. So the temperature rises up over a 7-hour period of time. And then as clouds develop, and clouds act as an insulating blanket, certainly not a perfect insulating blanket, but they do inhibit cooling. So the cooling is occurs more slowly, starting in the early to mid-afternoon, and then continuing through the rest of the daylight hours and then overnight, and continues then on the left side of the plot, sort of picks up from where it left off on the right side, and the entire process starts again. This is an average day, so one average day is just like another. That's all I have to say about temperature, and now I'm going to continue with rainfall. And just as I began with a statewide picture before I got into the Treasure Coast specifically, I'm going to begin with the average rainfall for the state as a whole. It's about 54 inches. But as you can see from the color-coded map, it might be a little tough to read the scale, so I'll help you through that. But the state is color-coded. The blue areas are relatively high precipitation, 60 to 62 to 64 inches or so. The purple is even higher. That would be like 66 to 68 inches of rain per year. That's just a dot, so it probably got put there by the weather records from one weather station. I don't know why the Panhandle, the outer part, the western part of the Panhandle is especially wet. It would seem like any place close to the Gulf of Mexico, which is a big moisture supply source, would also be wet, but that just does not seem to be the case. So the Panhandle takes the prize as being the wettest part of the state, and the second wettest part of the state is in the southeastern part of the peninsula, down in the Miami, Fort Lauderdale, maybe up to West Palm Beach. Why that green area does not extend all the way up the peninsula, I don't know, but the observations are showing that the rainfall is higher in the Miami area and extending inland a few tens of miles perhaps. Homing in now on Fort Pierce. This is a very ragged plot, and that's just another way of saying that Fort Pierce has some relatively wet years and has some relatively dry years. I have put a dotted green line at a annual rainfall rainfall total of 60 inches. That was just chosen by me. You could choose 61 inches or 65 or 59 or 58. You could choose whatever line you want for distinguishing between the wet years and the really wet years. And then down at the other end of the plot, the bottom of the plot, I have put another dotted line, a dotted blue line in this case, at about 47 inches. And that's an arbitrary cutoff, one which I chose to distinguish between the wet years and the really wet years. Most of the time, the Fort Pierce annual rainfall totals will be between those two lines, and it's just occasionally, maybe 10 or 12 times over the last 125 years, just occasionally that we will have really wet years or really dry years. In our state, and as I'll show in the next slide, in our Treasure Coast part of the state, we have distinct wet seasons and dry seasons. I've highlighted the wet season. It's a 4-month period of time, June, July, August, and September. And the blue bars definitely stand out above the red bars leading up to that part of year and then continuing after that part of year. The wet months, the 4 wet months, have between, well, maybe just under 7 inches to about 7.5 inches of rain per month, statewide average. During the dry season, then, the red bars during the first 5 months and during the final 3 months, the red bars are all between about 2.5, I guess November is the driest month at about 2.5, maybe not quite 2.5 inches. Between 2.5 inches and then almost 4 inches for May and October. Homing in on our part of the state, this is now the Treasure Coast and the Space Coast. I have included Melbourne to make this just a little bit more general. But we also have a wet season and a dry season. The difference between our wet season and the wet season for the state as a whole is that while Florida in general has a 4-month wet season, we have a 6-month wet season. So we've got 4 months relatively dry coming into and through April, and then the rainfall totals increase for the next 6 months and then drop off quite dramatically from October into November. In fact, if you add up the rainfall we get during the Dry season, we get 30% of our rainfall during half of our year, half of the 12-month year. And the wet season, then we get the other 70% of the rainfall in the other half of the year. So much for precipitation. Let me continue with the Treasure Coast winds. I think there is enough to say here so that this should be a part of the characterization of our climate. I'm going to start talking a little bit about the wind directions, and then I'll have a couple slides on wind speeds. Now, to characterize wind conditions, we use what are commonly known as wind roses. And you can see one wind rose in the lower left, one in the lower right, and presumably these little slices, like slices of pie that stick out from the center of the figure, presumably those should look like rose petals. I don't think they look like rose petals so much. I think they look like slices of pie. So I'm going to be referring to this just in this introduction. I'll be referring to this informally as wind pies. You won't see this written anywhere. It's just to help me make the point. And I have two wind roses or wind pies in the lower left. There is one that has all of the wind directions broken down into 8 octants. And in the lower right has another 8 octants, but as we will see in just a moment, the seasonal changes from one representing summer and one representing winter can be quite dramatic. In the summer slice of the pie, the octant representing winds out of the southeast is clearly dominant. In a respectable second place, we have winds out of the south, and I guess almost tied would be winds out of the southwest or the east. So that's where the winds are most commonly occurring during summer months. Winds out of the northwest are considerably less frequent. That's just a smaller slice of the pie. Winds out of the northeast are even less frequent, and smallest of all is the northerly octant. You can see it, but it's just barely visible, meaning that winds out of the north are extremely rare during summer months. Shifting over to the figure on the lower right, we have the wind rose or the wind pie representing winter months, and the picture there is significantly different. The octant representing winds out of the north is clearly the dominant one. Winds out of the northwest would come in second place, and these are the winds that follow behind cold fronts. We see from the other 6 octants that we can have winds out of the rest of the directions around the compass, but they are definitely of secondary importance. I was able to get wind observations from Cape Canaveral. This is also part of the Space Coast. I wasn't able to find this for Fort Pierce or Vero Beach or Stewart along the Treasure Coast. So using Cape Canaveral winds, which are probably quite similar to the winds that we have down here, I have plotted the average wind direction. These are the arrows that go up and down over on the left side of the plot. Starting with January, we see the average wind direction is out of the northwest, blowing toward the southeast, but it's out of the northwest. And then for the next 2 months, winds swing fairly gradually into the north. They blow out of the north. This is on average, of course. We have seen from the wind roses that we can have winds out of other directions. But the average, the dominant wind would be out of the north during February and March. And then it makes a very abrupt more than 90 degree switch from March into April, and stays out of the east then for May, and then completes the swing around, and we have average winds out of the south in June. So there's a clockwise turning of the wind direction during the first half of the year. During the second half of the year, things pick up from where they left off during the first half, and July has a continuation of winds out of the south on average. Day to day, of course, that would be the weather, but day to day, today we can have winds out of any direction. It's just that it doesn't happen very frequently. And then winds back up, and they swing out of the east and then out of the north in October, and then back to where we started from in November and December. So we don't have winds swinging all the way around the directions of the compass. They swing halfway around during the first half of the year and halfway around back the same way during the last half of the year. Now, in terms of wind speeds, the strongest winds, at least in terms of the monthly averages, occur in spring, March, April, and May. And I think we'll see in the next slide that March is the windiest month, but not by much. Winter, actually throughout the year, the average monthly winds don't vary all that much. Spring, we will see, stands out as the strongest winds. Winter runs a close second. Fall is in third place, and then things are relatively quiescent, not calm by any means, but relatively quiescent in summer months. Of course, that's when we have hurricanes, and hurricanes are anything but quiescent. But hurricanes are weather, not climate. There's no averaging involved in hurricanes. Now, showing the wind speeds, the monthly average wind speeds on this bar graph. Again, I've highlighted the March, April, and May wind speeds. They are the strongest, not by much, but they are the strongest. And March is the windiest month with an average wind speed of about 9 miles per hour. We can see that in the fall and winter, maybe the winter would be in second place, and then the fall would be in third place. In last place, with relatively weak winds, are the 3 months, June, July, and August in summer. Using the same meteorological data that we used to trace out an average daily temperature rise and fall, we can do the same kind of averaging and come up with a daily wind speed rise and fall. Again, I took all of the midnight temperatures and averaged them, 365 midnight temperatures, then averaged all of the 1 a.m., 2 a.m., and so forth through the entire day, and plotted that. And what we see then is the curve shown here by the 24 hourly bars. An average day begins with the wind decreasing slowly, and it reaches a minimum at about 7 o'clock in the morning, and then picks up over the next 7 or perhaps 8 hours to reach a maximum in the afternoon at 2 o'clock, 3 o'clock, and 4 o'clock. That's when we have our windiest time of day, and then the wind speeds start to decrease slowly through the end of the day, and they pick up then at the beginning of the next average, or the beginning of an average day at the left side of the plot. Now, that's all I have to say about wind. I do want a couple slides here about relative humidity, because relative humidity goes a long way in determining how comfortable or uncomfortable we are at any given time of day, at any given time of the year. What we will see, however, is that the rise and fall in relative humidity over the course of a day is considerably larger than the rise and fall in relative humidity from 1 month to the next. On an average day, the humidity will decrease from a maximum in the early morning hours to a minimum in the mid-afternoon hours. But from 1 month to the next, if we average over the course of a year, we'll see that there's not that much of a change from one month to the next. And that's what I am showing here. The red bars are the maximum relative humidities in the morning. We can see that they're usually around 85 to maybe 90% relative humidity. But as the temperatures warm up, the relative humidity goes down, and the afternoon relative humidities then are somewhere around 55 or 60 or maybe 65%. So on any given day, and that's true throughout the year, the early morning highs are significantly higher, stand out above the mid-afternoon lows. But if you go horizontally from left to right throughout the year, you see a seasonal variation, but there's not really that much. Now, this is a very useful plot. It's going to take a little explaining, but insofar as humidity determines comfort, I think it's worth the time. Now, I have chosen a day to use as an example, and I'm going to choose December 31st, which is at the far right-hand side of the plot. And I chose that day just so I'd have room off the plot to put in these percentages. You can see that in the main part of the plot, there's a color-coded region when the humidities are very high, and the person who did this plot called it miserable humidity conditions. A little bit lower humidity, it's not miserable, it's just oppressive. Lower than that would be muggy, but maybe tolerable. And then comes humid, comfortable, and dry. Now, going back to December 31st, we can see that at that time of year, about 5%, I'm using the scale over on the left side of the plot, but about 5% of the time, on an average December 31st, we have oppressive conditions. It's that pink color representing oppressive conditions. 27% of the time, it is either oppressive or muggy. And since 5% was oppressive, it must be 22% that is contributing to the muggy conditions. And then you can work your way up the plot from 27 to 46%. Another 19% of the time on December 31st, we have humid conditions. And then during another 14% of the time, we have comfortable. And then finally, the remaining 40%, it would be considered dry. Now, you can choose a different day of the year and just slide that vertical bar over to your day of choice, and the intersection of the miserable, the oppressive, the muggy conditions will shift accordingly. But for your day of choice, you can find out how much of the time, in terms of climate, on average, how much of the time the day would be miserable if you're in that part of the plot, or just oppressive or humid or comfortable. Or this is a useful plot. Cloud cover. Now, this is the last topic that I want to cover, and it's also the most difficult to cover, and you will see why in just a little while. Maybe it's not a good idea to end a talk in a way that's tough to characterize climate, but cloud cover is difficult to characterize. And I've given you two extremes from the two figures shown at the bottom. The left-hand figure shows the middle part of the Florida Peninsula, and we can see puffy clouds, certainly partly cloudy and maybe even mostly cloudy in some regions. But we see also, if you look carefully at the coastline, we see that the cloudy conditions are restricted to the overland areas. If you go a little bit off to the east, which would be off to the right, over the Atlantic Ocean, is completely cloud-free conditions. So if you were standing at the coast, or maybe even anywhere in Fort Pierce or Vero Beach, in that very narrow band, if you look off to the east, you would see completely clear skies out over the ocean. But if you look off to the west, you'd see partly to mostly cloudy skies. So how do you characterize the clouds? Well, it just depends upon where you are. The figure in the lower right, this is probably a picture that was taken from space right after a cold front came through, and the cold front brought in cool, dry air, and as a result, clouds have trouble forming in cool, dry air, so the entire peninsula is cloud-free. On the other hand, as that cool, dry air moved out over the Gulf on the left side of the peninsula, or over the Atlantic on the right side of the peninsula, it started picking up moisture, and because the water is warmer during winter months than the land, it started picking up heat, and with moisture and heat, now we can have cloud formation. And so insofar as there are clouds in the picture on the right, we see that they are restricted to the over water areas. So how do you characterize cloud conditions? Well, it depends upon the meteorological situation. And that brings me to the end of what I want to talk about here. We started, this is just a wrap up here, we started distinguishing between weather and climate, and I have mentioned a number of times since then, whenever talking about an average condition, that would be climate. We got into temperature, and there were no surprises there. It's what you would expect. We have hot summers, we have pleasant winters. I did, however, mention the urbanization process. Fort Pierce is getting warmer as it grows, but that's not global warming, that's not regional warming, that's just an effect of urbanization and more parking lots and streets and more runoff from those paved areas. And that runoff means that the moisture that falls as rain does not stick around to evaporate and cool the air. Rainfall, we have distinct wet seasons and dry seasons. We saw a 4-month wet season for the state as a whole, a 6-month wet season for the Treasure Coast. Winds, there wasn't a lot of variability there, but we did see that spring and especially March was the windiest month. Humidity varies much more over the course of a day between the early morning maximum and the mid-afternoon minimum than it does month to month over the course of a year. And then I just ended talking about cloud cover, and if you average cloud cover, given that there are clear conditions and cloudy conditions on other days, if you average that, what you end up with is partly cloudy. And so the only way to characterize cloud cover in space and in time is to say that we have partly cloudy conditions pretty much everywhere, pretty much all of the time. But the real action with cloud cover is in the meteorological condition that produced it. And that's where I will stop.